This is the second part of the NMR, and now in this case we will start talking about the number of signals, a little bit more about chemical shifts, coupling, and integration. So we will cover almost everything regarding the proton NMR. So just to review again regarding the chemical shift and the number of signals, if you have equivalent hydrogens, they will come at the same chemical shift, which means if they're in the same environment, that means they're in the same magnetic field, they're being exposed to the same magnetic field, they need the same amount of energy to align against the magnetic field. So they will come at the same chemical shift also, all right? And then, of course, we've talked about the fact that you can have shielded and de-shielded protons. So this is the de-shielded or the downfield region, and this is the shielded, which is the upfield region. So you have these two regions, and then, of course, the chemical shift. So here is a compound, okay, and don't worry about the functional groups. The whole idea is to create different environments here. So here you have a T-butyl group where these three hydrogens, these three methyl groups, they're completely isolated from the other hydrogens, so they are in their own environment. All of these three methyl group hydrogens, all these 9 hydrogens are going to be the same because they're in the same environment. They're all attached to a carbon which is attached to an oxygen. So they will appear as one signal. Then going on to the left-hand side where we have, see these CH2s here. This CH2, both of these hydrogens are going to be the same, they're equivalent, and they appear over here. And then we have the CH3, again, this methyl group is completely isolated, and so this will appear over here. And it is very different also from this 3 hydrogens, okay? So we have these 3 different environments. So you see 3 different signals. The second thing is about the shielding and the de-shielding over here. Looking at all of these different environments, we can see that the C protons over here, these 2 protons here, are in between 2 carbonyls, which makes them the most de-shielded protons, and therefore they appear in the most de-shielded region. The T-butyl protons, okay, over here, they will appear as the more shielded because, first of all, you have so many electrons over here. The only reason they are shifted a little bit to the left, usually methyl protons will come around 1, okay, or below, but they are shifted a little bit to the de-shielded region because of this oxygen, okay, but otherwise they're still quite shielded, okay. And then the CH3 here is next to the carbonyl, so it comes traditionally at around 2.2, 2.3, and which is right here. So here you can see clearly that you have 3 environments, and then you can clearly see the shielding and de-shielding going on in one simple NMR. Here is another one. This is a benzene ring, and here you have 2 methyl groups, okay? And in these 2 methyl groups, this benzene ring is perfectly symmetrical. If you can see, there is a symmetry going vertical, and then there is also a horizontal symmetry, okay? And so you have 2 different environments, one for the 2 methyl groups, and then one for the 4 protons and the benzene ring, all right? And again, benzene ring comes around to 7.2. So that's where you see the benzene protons, and then the 2 methyl protons are going to be down here. Now, because these 2 methyl groups are on the benzene ring, it's going to be slightly downfield shifted, okay? Because remember, they should come around 1, but they're coming more than 2 because of the benzene ring, all right? But they're all coming together. The line that you see over here, this one, this curved line that you see here, that is the integration line, okay? And we will talk about that. And this integration line shows you that there are 4 hydrogens underneath this area, and underneath this peak, you have 6 hydrogens. And here is our good old TMS. So the intensity of the signals, okay, which is called integration, which I started mentioning in the last slide, is the area under the peak, okay, and is proportional to the number of protons, and that is shown by the integral trace, and the trace was the curve that actually went from the signal, okay, it was on the signal. What you do is generally you have to run the integration yourself. There are a lot of things you have to do yourself in the NMR. The NMR scan that comes out will only show you a line with your spectrum. That's it. It doesn't give anything else. You have to set the scale, and then you have to set the integration when you're actually working on the instrument, okay? But usually when you're interpreting an NMR, you will be given a lot of this information. All right. So for example, in this case, you see this blue line over here. That is what the integral scale is. So when you press, say, I or integral for NMR in the computer, it will give you this line. What you have to do then is you have to decide, okay, I may have 6 protons over here, or I may have 9 protons here. Okay, so that's how you will decide. Previously, what used to happen before computer times and before such good integral systems is that you would have to sit and count the number of squares you would have this, because this would be a graph paper and you would count the squares and then you would figure out the ratio of the two peaks. But now you can do the calculation right on the computer, and so then it tells you, okay, here we have a ratio of 2:6, which is 1:3, and that's what you have here, 3 protons versus 9 protons. Okay, so the ratio of this integration to this peak over here is 1:3. This is kind of similar to the other spectrum that we just saw, where you have a T-butyl group and a methyl group. So the methyl group is coming downfield shifted over here because of the oxygen, and the T-butyl group is quite shielded because of the electrons, and it's coming around 1.2 ppm. All right, but of course this NMR is about showing you the integral that we can draw. So now we get into what we call coupling, which is also called signal splitting or spin-spin splitting. And this is the most interesting part about the NMR. Until now, we were seeing signals which were like this, okay, just singles. But now we get into things where signals start to split, okay? So for example, if you look closely into this signal, which is actually an expanded version of this one, it is shown over here, is that this signal split into two, and you know it's split into two and they're not two signals because this little dip does not come all the way down to the baseline, okay? And so you know that it has split into two. This is called a doublet. This signal over here with the pink one, this is been expanded over here for you, and this is what we call a triplet, okay? And this is a 3 signal splitting. So when the splitting starts happening, then you really start to understand the structure of a compound. Until now, all we could tell is how many different hydrogens we have. But once you start getting splitting, then you can tell exactly which hydrogen is next to which hydrogen, all right? So the way the signal splitting works is that if there are unequivalent protons next to each other, then you will see signal splitting, okay? Well, unequal protons means that if you have different protons, which also then appear at different chemical shift, okay, then you will see signal splitting. That's why you can see signal splitting over here. If they were coming at the same chemical shift, it would be hard for you to see. And if they were all equivalent protons, well, you will not see the coupling at all, okay, in those cases. So they have to be different. The signal splitting is usually for the proton, looking at the neighboring plus 1. Okay, so I'll explain that to you in a second. All right, so signal splitting is for the proton that's going on, and then it's looking at the neighboring proton plus 1 splitting. And that's why it's called coupling, because you're just looking at the neighboring proton. All right, and so this splitting has to do with the alignment of the protons to the magnetic field, because remember we talked about how the protons can be aligned with or against the magnetic field. So depending on how many protons there are, the protons can be aligned differently. So we'll explain that in the next slide, but right now I just want to show you a little bit about how the splitting worked here. So here we have this compound, which is CCl2H. Okay, there's only one hydrogen on the first carbon, and there are 2 hydrogens on the next carbon, okay, with 1 chlorine. So looking at this molecule with what the information we have so far is, we know that we have 2 different kind of protons, so which means that we should have 2 signals. We know they're going to be very much downfield shifted because we have all these chlorines there. So the signals are very much downfield shifted. Okay, so now let's talk about the splitting that's going on. For proton A, which is a single proton over here, this is proton A. Okay, the single proton, which is given by the integration also. So the single proton over here is coming as a triplet. So how is it coming as a triplet? It's coming as a triplet because it's looking at the neighboring hydrogen, which is 2 plus 1. Okay, so which means 2 plus 1 gives you a triplet. So it's not itself giving you a triplet, it's looking at 2 plus 1 to give you a triplet. All right. The blue ones over here, these are 2 hydrogens which are appearing over here. The 2 are not, this is not a doublet because of the 2 hydrogen. It just happens to be 2 hydrogen. But this is splitting into a doublet because this is looking at a hydrogen plus 1. Okay, so it gives a doublet. All right, and this has to do with the alignment of the protons in the magnetic field. It will become clearer in the next slide. Okay, so remember again, it's what is looking at the neighboring carbon, not what it is itself. Okay, so let's look at the neighboring effect and let's look at all of this alignment stuff that we talk about. So here is also another neat compound, very small and very symmetrical also. Okay, if you look at this one, we only have 3 carbons, plenty of chlorines, and here you have these 2 hydrogens that are equivalent and then this 1 hydrogen that is different. Okay, here. So this hydrogen is looking at these 2 hydrogens. Again, you can look at the hydrogens in the same or different, but so long it's only 1 carbon over. Okay, and so this hydrogen is looking at these 2, so which means that this should give you a triplet. Okay, these 2 hydrogens which are the same, they're equivalent, they're looking at this hydrogen, so they should give you this hydrogen plus 1, which is a doublet. Okay, now the pink hydrogen here, this is going to be the upfield shifted, whereas the hydrogens, the blue ones are going to be more downfield shifted because they're attached to carbon with 2 chlorines. A hydrogen, the pink hydrogen, is attached to only a carbon with 1 chlorine, so it's a little bit more upfield shifted. Okay, so that's about the chemical shift. Now let's talk about why we see the doublets, okay, and the triplets. So what happens then is that if you're looking at a proton, the proton can be aligned with the magnetic field or against the magnetic field. There are 2 ways that it can be aligned. The other possible combination for one single proton or for 2 protons, which are shown over here, there are 2 protons, those 2 protons, B protons, okay, over here, these 2 protons can be facing in one direction or facing in the other direction. The other combinations possible is that a proton is facing in opposite directions, and then the other 2 protons can be also facing in other directions but in a different alignment. So all of these different alignments are possible when you're looking at these 2 protons only. This proton is a single proton. It's a single proton, so it's either facing or opposing the magnetic field. So that's why you have only 2 alignments for the single proton. But when you have 2 protons, now you have these 3 different alignments possible. In fact, 4 different alignments possible. So these 2 alignments here, they're kind of similar. Why? Because you have 1 proton that is facing, 1 proton that is opposing the magnetic field. Okay, and so these 2 are kind of similar. So at any given time, these are the different orientations you can have of protons in the magnetic field. So the interesting thing about this is not only just all of this facing that's going on, all of these alignments that's going on, it's also the ratio in which they are aligning. Okay, so for example, the ratio of the alignment of with and against the magnetic field is 1:1, whereas where you have the combination of 1 facing and 1 opposing is 2. So now you have a ratio of 1:2:1. Okay, and that is what a triplet is. When you look at a triplet over here, this is how you see the alignments. 1:2:1. It's a very symmetrical kind of a thing. Okay, it's very pretty, it's beautiful, very symmetrical and very logical. Okay, whereas the alignment over here for a doublet is going to be just about 1:1 because you can have either that 1 proton facing the magnetic field or it could be opposing the magnetic field. So you only have 1 alignment on either side, so which means that you have 1:1 ratio, so which means that the doublet is then equal. Okay, 1:1 ratio, whereas the triplet is going to be a 1:2:1 ratio. This is how the coupling works. Okay, and this is what you see in the magnetic field. Here is the one for a quartet. Okay, so here is a CH2, CH3, and there is a bromine over here. This is ethyl bromide. So these 2 protons are looking at these 3 plus 1, so it will give you a quartet right here. And these 3 protons are looking at these 2 plus 1, so they will give you a triplet, okay, which is over here. The hydrogens that are attached to the bromines is going to be the downfield shifted, which is right here. The blue one is downfield shifted. The pink one is farther away from bromine, so it's upfield, okay? That's one thing. Then let's talk about the triplet and the quartet. So you already saw how the triplet occurs, okay? The triplet occurs because those two protons can have the three different orientations. When you have three protons, in the three protons, you can have these four different orientations. One in which case everything is aligned, one in which everything is opposed to the magnetic field, and then these two other combinations where two are aligned, two are opposed. Okay, and then you can have all of these different combinations going on here. So now the ratio of these alignments is 1:3:3:1. Okay, that is what the ratio is. So when you look at the quartet, again, it's a very symmetrical signal. So you have 1:3:3:1. That is how you get the signal. Whenever you have a triplet, the triplet would always be 1:2:1. If you don't see a 1:2:1 triplet, that means you have a mixture of signals going in there, which means you have overlapping of signals going on. Otherwise, a triplet has to be this kind and a quartet has to be this symmetrical and this kind. All right, and so that is how the signal splitting occurs. So always remember, it's not about the proton itself, but what it is looking at. All right, that is what the important thing is. So these two protons are looking at these three hydrogens plus one, that gives a quartet, and these three hydrogens are looking at these two plus one, and that gives you a quartet. Okay, or excuse me, a triplet then. Okay, and so that is how the orientation occurs. It's about what this proton is looking at, not what this proton is, but what it is looking at. So here's a nice little chart for how these signals appear. So if you have a singlet, it means that you don't have any kind of splitting going on, okay, because everything is equivalent and they are just facing in one direction. If you have one proton, that proton could be facing with or against the magnetic field. Okay, and by the way, the 0 over here, it means that all the protons are equivalent. Okay, so if you have one proton, that proton will give a doublet, which means it can be facing with or against the magnetic field, and then you get the ratio of 1:1. For a triplet, which you will get for two protons, the ratio is 1:2:1. Okay, this is also the splitting that you see, by the way. Okay, so for two, you will see a triplet. For three protons, you will see a quartet. It's always n+1 system. Okay, so you'll see n+1 peaks. So if a proton is looking at 1, it's looking at 1+1. Okay, if it's a proton is looking at 2, it's looking at 2+1. So that's how you're looking at all of these splitting that's going on. All of these splittings, they have very specific names. So you have a singlet, which is no splitting, a doublet for 2, triplet for 3, quartet for 4, quintet for 5, sextet for 6, and then septet for 7. And look at the 7. It's beautiful. When you see a 7 in the NMR, it's very, very clear of the fact that you have 6 protons. There is nothing else that is going to give that kind of a splitting, okay, when you see a septet. Septet and quintets are really fun to see because they're very symmetrical and just very pretty to look at. Okay, so that is how you would see the splitting, okay, that goes on. So a little bit more about the splitting so that things are clear to you. Equivalent protons do not split each other, okay, which is what is 0 over here. So if you have CH3, ethane, those two CH3s are alike, so which means that they're not looking at something different, so they're not going to split, okay, each other. So the protons bonded to the same carbon will split only if they're non-equivalent, okay? So CH3, CH2, as we saw in the other one, the three CH3s that you have, the methyl CH3s and the CH2, those two carbon hydrogens, they are not looking at themselves, they're looking at what is next to it. So nothing is going to split with whatever hydrogen is on the same carbon. You're looking at the neighboring carbon. So the only way the proton is looking at the same carbon is when you have two different hydrogens. We'll see an example of that later on, okay? Otherwise, you're only looking at neighboring carbons, not at itself. Only protons and adjacent carbons will couple, okay, which means that if you have something farther away than one carbon, it is not going to couple, all right? And then protons separated by 4 or more bonds will not couple, which is exactly kind of what we just said. Okay, only adjacent carbons will couple. So the adjacent can be on the left and on the right hand side. Okay, or they can be on one side. If there's only protons on one side, then that's it. But if you have protons on both sides, then you will get splitting from both sides. Sometimes it can be a mess also, but most times hopefully it'll be nice and pretty. Okay, so let's look at the spectrum over here. This is for a nitrile. This is CH3OCH2CN, which is a nitrile compound, and then there's an ether also. What this spectra actually signifies is that as soon as you put an oxygen in between these two carbons, now these two carbons are separated by a heteroatom, and then no splitting will occur. Okay, so the carbons have to be next to each other for splitting to occur. That is what I was trying to emphasize in the previous slides. Okay, so it has to be a neighboring carbon thing, the next carbon over. So no splitting over here. You will see the two signals, no problem. You will see the integration for 2 and 3 hydrogens, no problem. Okay, that's fine, but no splitting. Okay, so now let's look at a little bit more of the signal splitting. Okay, in the previous one we saw that you could not see splitting if there was a heteroatom in the middle. Here we have ethyl benzene, so here are the benzene protons and here the CH2 CH3. As soon as you have a CH2, then you know you're going to get a quartet from the next one. The CH3 is going to look at a triplet for the next one. So that is what you see in the spectrum here, a quartet and a triplet. All right, and then the benzene protons, they're going to come as a mess, and this is actually called a multiplet. Okay, and the multiplet here indicates that there is no clear pattern of how things are visualized, because these 5 protons over here, they can be aligned in very different ways in the magnetic field, but there is no clear proportion to it, and that's why you end up getting a multiplet. Sometimes, in some cases, you will see very nice splitting even for the benzene ring. Okay, and if we come across one, I'll show it to you. But otherwise, benzene ring protons can be usually a mess. Okay, and that's why they're called multiplet. So for ethyl benzene, you will have 3 signals, and then you will have the quartet and the triplet. Okay, going on. The triplet, which is coming from the CH3, is going to be a little bit more upfield because this is a CH3 protons, and CH3s come around 1 ppm. Okay, let's look at another spectrum over here, and this is the one for isopropyl group. Okay, and this is really fun because this is the one where you have this the 6 protons. So when you have 6 protons, 6 equivalent protons means 6 plus 1, which means a septet. Okay, that's what you will see. So the neighboring carbon here, this was one single proton. This single proton is looking at 6 plus 1 to give you a septet. These 6 protons over here are looking at this 1 plus 1 to give you a doublet. Okay, so isopropyl groups are characterized by a doublet and a septet. All right, so let's look at the spectrum here. Here is your septet, and here is the doublet. The doublet is going to be humongous because the doublet is actually 6 hydrogens. The septet is going to be really small because the septet is only 1 hydrogen. It's looking at 6 hydrogens, but it itself is only 1 proton, the poor thing. Okay, so this here is an expanded look at the septet. And you can clearly see how the ratio is working here. These 2 little things on the side, they also count as part of the ratio. Now remember, everything is above the baseline, and that's why you know that it is actually a signal splitting and not different signals. So 1, 2, 3, 4, 5, 6, 7. Okay, that's the septet that you see. And then the CH3 here is isolated. There is nothing next to it to couple with. So this CH3 is going to come as a singlet. Okay, so as you start seeing splitting, things become a lot more interesting, as I said, and then you can really analyze your compound and come up with a structure, okay, very easily. These 2 spectra over here, I want you to keep this in mind because this is a really good tidbit in analyzing spectrum, which means that if you see a triplet and a quartet, In your spectrum, a triplet and a quartet would generally mean an ethyl group. If you have a septet and a doublet in your spectra, that means you really have an isopropyl group in there, okay? And so that's how we look at these patterns in the NMR and then try to decipher our compound. So here are some problems that you should work with on your own, okay? And again, you should look for those patterns, okay? So for example, here is a nice looking septet and a doublet. So here we just talked about that. So you can figure out the structure for this one. Here we have a quartet and a doublet, okay? But this is the molecular formula you have to work with, all right? So C2H4Cl2, you have to put them in such a way that they couple to give you a quartet and a doublet, okay, which means that you should have a single hydrogen and you should have 3 hydrogens that are the same. And then solve this one also. I will not give you any clues for this one. You figure it out yourself. Because of coupling, then we come to something which is called a coupling constant, okay? Because if you have a complex molecule and you have a lot of coupling going on between different hydrogens, then how do you know which peak is coupling to which one, okay? Which doublet belongs to which triplet, triplet belongs to which quartet, and so on and so forth. So if it becomes too complex, then you start looking at what is called the coupling constant. The coupling constant is the distance between the peaks of the multiplet, okay? So this distance right here in the middle, that is called the coupling constant. So now you're really getting into the minuteness, okay, of NMR, and this is where it becomes even more useful than it has been until now. So if you look at this molecule here, which is a very simple molecule, yet again you have the 2 hydrogens here and the 1 hydrogen here. When these two couple, you will get a triplet and a doublet, okay? The triplet and the doublet that you get from this particular combination of atoms will have the same coupling constant. So when you look at that triplet and that doublet in an NMR spectrum, the distance between the 2 peaks that are splitting will be exactly the same. Okay, so J, that is called the coupling constant. JAB over here is going to be the same as the JAB over here. Okay, so it's not the distance between end to end, it's actually the distance between each of the splitting, okay, that's going on. This is usually measured in hertz because now we're getting into very small numbers, okay? We're not looking at ppm anymore, we're looking at very small numbers, so it gets into hertz. On the next page I have some numbers there for you. It doesn't depend on the strength of the external field. It doesn't matter whether you're talking about a strong magnet or a weak one, it doesn't matter. So in any case, so that's what coupling constant is. So here are some coupling constants for some of the compounds. So for example, if you have a free rotation CH-CH, then this is kind of what you will see, 7 hertz, which means the distance between the 2 peaks, the splitting, is going to be 7 hertz. When you have something like this, which is a double bond in case of cis and trans will show different kind of coupling constant. Okay, so you have 10 and 15. So really it's very good, okay, for cis and trans bonds, okay, to use NMR to figure out if you have cis or trans, okay. And then geminal hydrogens will have 2 coupling constant, which is really very small, okay. So here are 3 different kinds of combinations of hydrogens that are possible. Remember we said before that if you have the 2 hydrogens on the same carbon, they will not couple. Well, in this case, they will couple because this is a double bond and double bonds do not rotate. Okay, and if they cannot rotate, it means this hydrogen has its own environment and this hydrogen has its own environment. Depending on what is on the other side of the double bond, these two may be equivalent or not equivalent, okay? So this number here, this value is assuming that these two are non-equivalent at this point. So if they couple to each other, then you will have a distance of 2 hertz in between the splitting, okay, that's going on. The splitting for benzene for orthoprotons is 8, for meta it's 2, okay, so this is really far away. Anyhow, so this is how you would see these numbers. Now, technically speaking, at this level, we don't do so much with coupling constants, but you just get an idea, okay, of what this is about. And so you can see how we can use NMR to figure out the exact structure, okay, and coupling going on in an NMR. So when I said that you can have different compounds will give you different coupling constants. So you saw these two splittings before, okay? But I just want to mention this to you that if you have a compound like this, okay, where if you had Cls over here, this proton is in a different environment than this proton which has CH3s over here, and if there were two chlorines over here, it would be a different environment for it. So the coupling constant then for these two will be different, okay? And so when these two protons A and B are coupling, it will give a different coupling constant, and when these two here AB are coupling, it will be a different coupling constant, okay? So that is how you can tell what is coupling and what is not. So really when you have a complex spectrum, that's when you need this. So complex spectrum number 1. All right, here we have styrene, which is called vinyl benzene also. And in case of vinyl benzene, okay, we have 3 different protons, okay, and this is a double bond. The double bond has 3 protons and then 1 phenyl ring. Now C and B protons, they're coming on the same carbon, so these are geminal protons. But the fact is that because of this phenyl ring, these two protons now have different environment. Also because this is a double bond and you cannot rotate the double bond. So B is in a different environment and C is in a different environment, which means that you will technically see about 4 signals, okay, for styrene. A, B, C, and then of course for the phenyl proton. So you have 4 signals and each of them will have their own splitting. So which means that A and C will couple, A and B will couple, C and B will couple. Okay, and so you'll have a whole lot of coupling going on, and then you look at the coupling constants and then you figure out, okay, you know what's going on, because all of the coupling for these A, B, C protons, these signals will be very close to each other. Okay, and if they're very close to each other, then it really takes a talented person to kind of go through it and sit and measure all of these coupling constants out and then figure out which proton is which one, okay, and where it is attached. So anyhow, this is the kind of splitting you will see. Here is the spectrum for styrene, okay, and as I said, you'll see 4 signals, one for the benzene ring, and then you will see the complex signals going on for A, B, C. So C is coupling to A and it's also coupling to B, okay? So C is coupling to A and B, which means 2 plus 1, which is a triplet really, which can't happen. You can't see that. But here are the C protons. The C protons, if you look at them, which is over here, I hope you can see it, but it is still splitting even more. Okay, so when C looks at A, it looks at a doublet. When C looks at B, it's looking at 1 proton, so that's a doublet. So which means you have a doublet and a doublet. Okay, but they're not that far away from each other, so the doublets are kind of like overlapping. All right, so if you look closely enough, you will see the doublets. So the same things happen for B. Okay, the B is looking at C and A, and so you end up getting doublets, okay, in there. So A, however, is giving you very clear 4 signals. The 4 here, the 4 splitting that is going on is the doublets, okay, that we have the 2 doublets and they're kind of overlapping. So that's how it gets to be a little bit complex when you start having double bonds in compounds, okay? And then of course look at the complex splitting that's going on for benzene also. This is not really just a multiplet anymore. This is a scary multiplet. Okay, so now let's go on just a little bit about some of the non-equivalent protons, okay, which means that where do you see this kind of a complex splitting going on? And the non-equivalent protons will come from something like styrene, as we just saw, okay, where you have restriction of rotation, or you can have it in cyclic compounds also, because in cyclic compounds also you have restriction of rotation. Or you can have it in these compounds, and the problem here of course is conformational analysis, okay, back from organic 1. So when you have restricted rotation here also, then you will start seeing these 2 protons which are on the same carbon, but you will see them separated out, okay, and so that's when you start seeing non-equivalent protons. So double bond, cyclic compounds, and then when you have conformers which are stuck in one position. The hydroxyl proton, this is an interesting one because when you start looking at the hydroxyl proton is separated from the other protons by 1 oxygen. So this is ethanol, okay, for example. And so this proton technically should be coming as a singlet, okay, which is over here. But in some cases, if you have a really, really good NMR and a really, really good sample of ethanol, then you will actually start seeing splitting for this proton also, okay? And so this proton now will split, okay, into more. So that's this one over here. This is the better NMR. So the triplet, the quartet, the CH2, CH3, that gives you the triplet and the quartet and the singlet. That is what you will see normally for ethanol. But in a really good sensitive environment, you will see even more complex splitting. So depending on your instrument, if your instrument gets better, then you start seeing more splitting. Okay, and so you have to be careful with that and know that you have a better instrument or you have a really good sample also. Okay. The NH proton, we talked about amines before, and the amines protons and the hydroxyl protons. The hydroxyl also sometimes come as a nice peak, but sometimes the amine protons and the hydroxyl protons will come like just a little bump, okay, in there. So it's a broad peak, but again, it's kind of sometimes hard to see, but you will see it, okay, so it's right there. The best way to tell whether you have a hydroxy peak or an amine peak, of course, is by exchanging it with D2O. I mentioned it before also. You put deuterated water in it, and then you observe if any of the peaks has disappeared in your NMR. Okay, so you take for the original sample, then you add D2O, and then you take the NMR again, and then you see if anything has disappeared. All right, and so that will tell you whether you have a hydroxy or an amine peak. A little bit about resolution. Okay, so here are two spectra, a 60 megahertz and a 300 megahertz NMR. 60 megahertz NMR, not such a good NMR, okay, because you're looking at a very low frequency over here, and the magnet, of course, here is not going to be very strong either. When you look at a higher megahertz or a higher frequency NMR, then you also have a better magnet. Okay, with a better magnet, you get a better resolution. And remember, when we talk about magnetic strength, it depends on the flip, okay, how protons are aligned with and against. So what happens with the better magnet is that the distance between the two alignments separates out even more. Okay, and so when the energy required is more, the signals become a lot clearer. Okay, with 60 megahertz and a very weak NMR or a weak magnet, you don't have that much of a difference in the energy, okay, and so things will start overlapping in such cases. But if you have a 300 megahertz or higher, then things will spread out a little bit more because now you have more distance between the protons. So here they have some overlapping of signals and the signals are going below the baseline, but in a good NMR, high megahertz NMR, you have a clear baseline and there is also no overlapping of signals. Remember, overlapping of signals is not only that you get overlapping of signals and you can't see the triplets and the quartets, you also mess up your integration. And then finally, one of my favorite things is the 2D NMR. You will probably not see 2D NMR unless you are in a graduate program with chemistry. And 2D NMRs are really fun, and this is a little bit more useful when you have complex splitting. So when you have complex splitting and you really don't want to work with J's, then you do 2D NMR, which is two-dimensional NMR. So you run the NMR in one direction and then you run it in another direction, and then you correlate the peaks. Okay, so you will see the same peaks on both sides. So here is 1.2 and here is 1.2. So you see a doublet here, you see a doublet here also. But what you also see is that this doublet is showing another little coupling with this multiplet over here. So it means that this doublet and this multiplet here are going to be coupling with each other. Okay, so you can look at all of these patterns. It's almost like flying over a mountain range. So when you fly over a mountain range, then you get a better perspective of where everything is, okay? Rather than looking at it from a ground where you see only one dimensional, if you look at it from the top, then you see a better perspective, okay? And so this is exactly what we see in a 2D NMR. So it's really fun when you start having complex molecules, then you get to run 2D NMRs. So for the key concepts for this little portion here, it's not little, it seems little, but really there was a lot of information in there. I want you to keep focusing still on the chemical shifts and the non-equivalent and equivalent protons and all of that. We did that in the previous presentation, but you still need to look at the chemical shifts. You need to look at the integration. You need to understand how each peak can have different areas under the peak. And then of course, coupling. Okay, you need to be able to analyze an NMR spectrum, or you need to be able to predict an NMR spectrum both ways. Okay, so I can give you an NMR spectrum and ask you, what is this compound? I will give you a molecular formula, you tell me what the compound is. Or I can give you a compound and then you tell me what the structure would look like, okay, or what the NMR would look like. It has a triplet and a quartet, and the triplet is downfield. And so on and so forth. Okay, I wouldn't worry too much about coupling constants and the complex coupling that I talked about. That was just a little bit more for your information, and maybe in some cases when you're working on an assignment you might see that, but I don't usually ask that on an exam. And of course no 2Ds on the exam.